Okay. Hello, everyone. Good afternoon to those of you Eastern time. Before I get started, I have a few announcements. So the deadline for Lab 3 is coming. Lab 4, 3. I think it is Lab 3. Yeah, so the deadline for Lab 3 is coming this Monday. Please make sure that you submit your peer reviews by the deadline, even if you want to use your grace days for lab 3. The deadline for submitting your peer reviews is the original deadline of the lab. So even we had, I think, 2 cases, 2 groups had late submissions of their projects, and they thought that they can also have late submissions of their peer review. But as I indicated in my notification email on peer reviews, the deadline for peer review does not change, and it's always the fixed deadline for the project. With regard to quizzes, the grades won't be released probably soon. It's very unfortunate that we have to deal with some cases of violations of academic code of honor. So we're doing a thorough investigation into previous quizzes. So there will be some delay in releasing the grades for quiz 5, and that's very unfortunate. Let me see if there's anything else. Yeah, I think that's pretty much all the announcement I had. So let's get started with the course and the lectures. Get rid of my video. Okay, so before actually I get started with the lectures, there was one really good question posted on Piazza that I think is worth mentioning during the lecture. So let me go back to the slides where we talk about different scheduling policies. Yep, so all 3 categories that you can see here, static scheduling, dynamic scheduling, and fully dynamic scheduling. All 4 categories belong to the class of online schedulers. So we have 2 types of schedulers, online and offline. So for offline scheduling, you need to know all the tasks that you're going to run your schedulers on. And you need to know every parameter about your tasks. So the tasks are set, their parameters are set. Let's say their deadlines, their execution time, all of it is set. And then you just come up with a schedule for your task set that says what task runs at what time. All of this happens before you even start running your tasks. Because you know about them, you can come up with a schedule. So that is offline scheduling, and that is not of our interests. So we're not going to talk about offline scheduling at all. Now, with online scheduling, you don't make any pre-assumptions about your tasks. So your tasks will come as you start running your system, and as they come, they make scheduling decisions. So that is online scheduling, which is basically all 3 categories here. They're online schedulers. Now, if you have an online scheduler, you can easily apply your online scheduler to a set of known tasks offline and produce a schedule. So that's fine. So you can use an online scheduler to do offline scheduling, but the other direction is not possible. So if you have an offline scheduler, that scheduler cannot be deployed in a dynamic setting or in an online setting where tasks come dynamically. So hopefully that is clear. So that's why when we talk about EDF, let me go. Yep. So as you can see, EDF is optimal with regard to all online schedulers. So basically, all three categories that we talk about. So any scheduler belonging to the category of online schedulers, EDF is optimal with that regard. Okay, so that was something to clarify. Now, what is the schedulability test for EDF? So for EDF, all you need to have is if the utilization of your tasks is equal to is less than or equal to 1. So the way to look at this equation here, it's very important to understand it. So EI divided by PI basically tells you the percentage of time that task I uses the CPU. Because task I appears every PI time units, and in every PI time unit, task I needs EI time units to execute. So EI divided by PI tells you how much this task is going to utilize your CPU. What percentage of CPU time will go to execute this task. Now, if I sum up all my tasks and it's more than 100%, obviously that task set cannot be executed by any scheduler because that would require more than one CPU to execute. So now you can see the power of this equation. This equation says if the utilization is less than 100%, then EDF can actually schedule that task set for you. And in a situation where we have utilization more than 1, we say that the system is overloaded. Now, what happens with overloaded systems under EDF? Unfortunately, although EDF is optimal with usual loads or schedulable task sets, when you have an overloaded system, then EDF might actually behave in a weird way. So this is one example. So I have 4 tasks. As you can see, the deadlines and the periods. If you sum them up, you can see that the utilization of the system is more than 1. So 3/4, 3/5, 3/6 plus 3/7, that would be more than 1. Now, what does EDF do in scheduling them? So the lowest deadline would be task 1, T1. So T1 will be scheduled first. It will run for 3 time units, and it will be done. Then we'll go to T2, T3, T4. T2 has the lowest deadline, which is 5. So we'll start running T2, and this will miss its deadline because it needs 3, and you have already hit 5. So this T2 misses. Then T3 starts and misses, and then T4 starts and misses its deadline. So basically only T1 meets its deadline. Now a better schedule would be something like this. So either run T1 and T3 or T1 and T4. At least you get 2 tasks or 2 jobs done instead of 1. You will still miss the deadline of T2, in this case T2 and T4, and T2 and T5, T2 and T3 in this case, but at least you can finish 2 tasks. So that's something to keep in mind. Now let's move on to the next scheduler that we want to talk about. It's least laxity first. So This one is a fully dynamic scheduler, which would assign priorities to jobs based on their laxity, which is based on their slack. So what is the definition of a slack? So at time t, if the deadline, absolute deadline, not relative deadline, if absolute deadline is d, and you have e time units remaining to execute your task. So if from your execution, e time units has remained, then your laxity or your slack at time t is the deadline minus time t minus the execution time. If I want to put it in picture, so at time t, if you start running your task and let it run for its remaining schedule, then it will finish at time t plus e. Now anything from here to d is basically your laxity. So laxity is d minus t minus e. And as you can see, the more laxity you have, the more flexibility system has in scheduling you. So if you have a task that has a laxity of 0, this basically means that you have to run that task right now. If you even wait for one time unit, you're going to miss the deadline of that task. Now, least laxity first prioritizes tasks with a smallest laxity. And as you can see, the laxity of a task changes, the laxity of a job. So if you have periodic tasks, so each one of them has jobs to come, each job, its laxity changes, and as a result, the priority of that job also changes. So if you want to, make similarities with this and multi-fair queuing. So in multi-fair queuing, we were pushing a job down the queues so that the priority of a job would, get lower and lower and lower. Here we are actually pushing a task up. As its laxity gets lower and lower and lower, smaller and smaller and smaller, the priority of the task is elevated. Until it becomes 0, then it's emergency. You have to execute that task if you want to meet the deadline. So you can actually prove that LLF is as powerful as EDF. So it's also optimal with respect to all online schedulers. But there is one problem, one big problem with LLF, which is very similar to shortest remaining task first. And that is it's impractical to implement it in real world. So here is an example. Let's say you have 2 tasks with different deadlines and different executions. Now at time 0, what is the laxity of task 2? So the deadline is 5, the execution time is 2, and t is 0. So the laxity equals 3. What is the laxity for T3? Is 6 minus 3 minus 0, which is also 3. So both of them have the same laxity. So at this point, we have to do a tie breaking. So let's say, so at this point, laxity is both 3. Let's say we start by T2 for a time unit. The moment we start running T2, T3's laxity goes up because we haven't executed it, so that the laxity gets smaller, and as a result, priority of T3 goes up, so you have to execute T3 next time unit. And then after this, you again get to a state where you have equal laxities. Let's say you switch to T2, then switch to T3. So at this point, both of them now again have laxity of 2.5. So you can do this again and again. So they keep getting the same laxity. And as you can see, depending on how big or how small your time unit is, your scheduling quanta, then you might actually have to context switch a lot. And this is basically not a plausible property to have. Okay, so this slide basically summarizes everything we have said. So rate monotonic is very simple. It's a static. EDF is optimal and practical. It might misbehave in overloaded conditions, but hopefully if your system is not overloaded, you should be fine. Least laxity first is also as good as EDF. It utilizes your system, but then it also misbehaves if you have jobs with equal laxity. Okay, so we're sort of done with three main scheduling policies that we wanted to talk about for real-time systems. Now let's talk about scheduling aperiodic tasks. So far we have focused on periodic tasks. So what happens if you have aperiodic tasks? So if you remember aperiodic tasks, they don't have a deadline, and they just come without any period. So they just show up to the system, and you have to take care of them. So one idea is to just run them as soon as they arrive. So give them basically the highest priority. The moment a job comes up periodic, you just run it, interrupt your periodic tasks. But as you can see, this might be very good for aperiodic tasks, but it could destroy all the guarantees that you have for your periodic tasks. So if you have a guarantee that your system is schedulable without aperiodic tasks, if you add this scheduling policy to your system and you introduce aperiodic tasks, then all those guarantees would be voided. Now, another idea is to basically give the opposite way. Give them the lowest priority. Whenever you're done with all your periodic tasks, come and run them. And this one is the one that you're going to implement for lab 4. But as you can see, this one, well, it's good for periodic tasks, but it's not that good for aperiodic tasks. A better idea, which we're going to talk about, is called periodically invoked servers. So the idea is to have a separate queue. So you have a separate queue for aperiodic tasks and a separate queue for your periodic tasks. So this basically the one that you have for periodic tasks becomes your ready queue, and then all the aperiodic tasks would be queued in a different queue. Now you would put a server here, an agent, a program that is going to take care of aperiodic tasks, and what it does is periodically this server will wake up. Now, how this happens, we'll talk about it. We're going to give this server a budget. So it's going to have a budget of BS and a period. So we'll assign a period to this server, and we will pretend that this server is one of our periodic tasks. So every time this server wakes up, every time it's its turn to be scheduled on CPU, it starts dequeuing tasks from this queue. And for each one of those tasks that this server runs, it pays some price from its budget until its budget is done for this period. And then it will be waiting for the next period to come to have its budget back. So I got a question. Why do we associate periodicity with a task having a deadline or not? So this is if you go back to the terminology that we defined for tasks. So we have another task class which is called sporadic. So with the sporadic tasks, you don't have a period, but you have a deadline. So basically, we have categorized our tasks to 3. So they have period and deadline. They don't have period. They don't have deadline. They do have deadline, but they don't have periods. So these 3. We haven't talked about the case where you have period but not deadline, but that doesn't make any sense, right? So if your task is going to come every period, you better be done with the previous one before the new one comes. So it's kind of like deadline is implied if you have periodic tasks. I hope that answered the question. Okay. Now, the first, so now how do we implement this server? It depends. So there are different ways to implement this server. And that would have something to do with the budget and the period. So the first one that we consider is called polling server. So basically what it does, I'm going to show it in a picture, in a figure here. Let's say you have a task T1 with period 4 and execution time 2. And let's say I'm giving my server, the polling server, period 2 and budget, period 5 and budget 2. So this is its period and this is its budget. Now, let's say that these are my arrivals for aperiodic tasks. So each one of them would come at a certain time. Each one of them is going to take a certain amount of computation. Now, this is arrivals. So let's see how a polling server executes these guys. So the way it works is that we're going to actually implement in this polling server scenario an RM, so rate monotonic. So because we're executing rate monotonic, T1 is going to have a higher priority than PS because T1 has deadline 4 and PS has deadline 5. So T1 always has priority over PS. So that's first put out. Now, every time it's PS's turn to execute, which is at this moment, it will look at the queue. It sees 2 tasks have already come. It uses its budget to run these 2 tasks. And once it's done, it yields the CPU. So it says, I'm done with this period. And we can now schedule any other tasks if there are any others. Now, let's say here, again, we run T1 because it has more higher priority. And at this point, we're again back to PS, polling server. But then polling server immediately wakes up, looks at its queue. There is nobody in the queue. So it will yield here again, because there is no work for it to be done. So then in this period, there would be no execution because PS woke up and there was no task in the queue. It polled the server, it polled its queue, there was no task, so it yielded. And it will wait for its next period to come. Now, let's say here at this point, again, we run T1 and now it's PS's turn. PS wakes up, looks at its queue. There are 3 tasks now in the queue. It can execute them. And again, the moment there is no task in the queue, it will yield. And so on and so forth. Now, if you look at this polling server, you might think, okay, why didn't I? So in this period, although I had a task, I never executed it. And here, although I still had time to execute this task, but I didn't. Why this happens? Well, it happens because of the nature of polling server. So polling server only yields when there is no task. So if you put it in the perspective of budgets, then you will have something like this. So this is basically the budget of a polling server. At the beginning of each period, your budget goes all the way up to 2, and you maintain that. And then once you start executing, your budget goes down as you execute tasks. The moment you have 0 tasks left, you basically get rid of all your budget. Your budget goes to 0. Again, at the beginning of your period, your budget goes up. You maintain your budget until you're scheduled. The moment you are scheduled and there is no task in your queue, your budget goes to 0. So at this time, the reason that we're not executing this is because our budget is 0. And it would be 0 until the deadline, the period comes. You again get a boost in your budget and you execute. The moment your queue is empty, budget 0, and you continue. Now, there is one way to deal with this to make sure that we actually run these two tasks potentially. And that is, well, what if we preserve our budget? What if we don't make our budget go to 0? Then you would have something like this. So for the same scenario, again, I'm showing. So if you preserve your budget, now you can actually run this task. And here again, so you run these two, you still preserve your budget. When the time comes and this guy comes, you can actually run it. So in this scenario, if you look at the budget, it would be something like this. So you get a boost, you execute some tasks, but then you keep your budget intact. You don't make it to go to 0. Again, here the same. Now you might actually think, okay, why here I have a budget and I have two tasks, why I'm not running them? So in this case, you're not running them because T1 has higher priority than you do. So T1 has higher priority, that's why T1 runs. So if you want to be able to run these two, maybe you should give DS a lower deadline so that DS has higher priority. So remember, for both deferrable servers, which is this case where you preserve your budget, and for the case of polling servers, we're basically running RM, rate monotonic. So we statically give priorities to tasks. Okay. The last one that I want to talk about is what if we don't use rate monotonic? Instead, we use something like EDF. So that would create another type of server, which is called total bandwidth server. And the idea with these servers is every time you get a task, you get an aperiodic task, you're going to artificially assign a deadline to your task. So you're going to put both periodic and aperiodic tasks to the same ready queue. But because your aperiodic tasks don't actually have periods, you have to artificially assign a period to them. The way you are going to do that is you always make sure that you assign a deadline because it's artificial. You can set any deadline you want. You set the deadline such that your system is not overloaded. Basically, maintaining the schedulability of EDF. So this way, your aperiodic task will be treated as a periodic task with an artificial deadline, and the system is still maintains its schedulability. One way to do this in dynamic systems, remember in online schedulers and dynamic ones, you really don't know what tasks are coming. So this is a perfect situation that we're seeing, the difference between online and offline. So in offline, you never can deal with aperiodic tasks, right? If you don't know when they're coming. But with online ones, the way they come, the moment they come, you can make a scheduling decision. Now, because you might not know how many aperiodic tasks you get, you could assign them all a maximum bandwidth. You could say, I want all my aperiodic tasks to utilize the CPU at most 10%. So basically, you want to allocate at most 10% of your CPU time to aperiodic tasks and 90% of your CPU time to periodic tasks. So if that's your goal, then you can use that bandwidth threshold to set deadlines in this way. So basically, when you want to set a deadline for task I, let's say aperiodic task I arrives at time AI, and it has an execution time of computation time of CI. then the deadline that we're going to assign, this is a artificial deadline, is going to be the maximum of the deadline of previous aperiodic task and the arrival time. So if this arrival time is after the deadline of a previous aperiodic, we'll just take the arrival time. But if this arrival time is before the deadline for a previous task that came before us, then we use the deadline of that task plus CI divided by UTBS. So this one here, CI divided by UTBS, will make sure that what we're adding to the utilization of the system is always less than UTBS. So you can do the math, because what we're adding is basically the deadline becomes the sort of the period, and the execution time is CI. So it's going to be CI divided by UTBS. So UTBS goes to the and becomes denominator, and CI's cancel. So what you're basically adding to the utilization of your system is at max UTBS, which is what we wanted. So here's an example. Let's say I have two tasks, T1 and T2, with this characteristics. So if you add the utilization of the system with T1 and T2, you will get that. So this one is utilizing your CPU 1/3, and this one is also utilizing your CPU 1/3. So what is remaining is another 1/3. So you want to make sure that UTBS is basically less than 1/3. So as long as UTBS is less than 1/3, you will and you follow this rule, your system will always be schedulable. So EDF can always make the deadlines meet. Make the tasks meet the deadlines. So here is an example. So for the same example that you see, let's use UTBS of 1/3. Now, task 1 is arriving every 3 time units. Task 2 is arriving every 6 time units. Now, let's say that we run T1, so there is no aperiodic task. So if there is any aperiodic task, I will put it here. Okay, so T1 has the least deadline, earliest deadline, so it will be scheduled. Then let's say at this point I have an arrival. So let's say the first aperiodic task comes. So A1 is 1 and C1 is 1. Now I use this formula. So there is no deadline. So this is 0, basically. So max of 0 and 1 is 1, plus C1 is 1 and UBC is 1/3. That gives me a deadline of 4. So I'm going to set the deadline to be 4 for this task. So now I have created an artificial periodic task, or a task with deadline, basically. Now the scheduler looks, it has T2 and this guy. So T2's deadline is 6. This aperiodic task's deadline is 4. So this task gets to be scheduled first, because EDF schedules the tasks with earliest deadline. Now at this time, we don't have any other task to run, so we run T2. Let's say at this point, another task comes. So A2 equals 3 and C2 equals half. Now you use this formula. D2 becomes maximum of 3 and 4, which is 4, plus half divided by 1/3. It would be just 5.5. So we set a new deadline here. Now at this point here, I have 3 tasks ready to be executed. I have 1 unit of T2 left, just 1 unit of T1 just came, and I have this new aperiodic task. If I look at their deadlines, the aperiodic task has the lowest deadline, so I will run the aperiodic task at this point, right? And then I go back to I have to do a tie-breaking rule between T1 and T2 because they have the same deadline. Let's say T2 wins the tie-breaking rule. I run T2 and T1 and so on and so forth. So if you want to follow this example, it has more arrivals and I've done the calculation for I think 2 more arrivals of aperiodic tasks. Hopefully this makes sense. Okay, I'll leave that to you to look into. Now, so let's recap. We talked about scheduling periodic tasks, all of it on a uniprocessor so far. Then we talked about scheduling periodic and aperiodic tasks. Now so far, we considered no interdependency between our tasks. So there was all the tasks were independent. Now let's assume that tasks are dependent. So generally speaking, deciding whether or not a set of periodic tasks with interdependency, in this case, let's say they are dependent because they're using semaphores to enforce mutual exclusion. So just deciding whether or not this task set is schedulable on a CPU, on a uniprocessor, is NP hard problem. So it's a hard problem to solve. Usually, we are dealing with a hard problem. Now, this hard problem gets exacerbated because of the way that we might implement synchronization. So far, in a lecture that we had on multi-threaded kernels, we saw how to implement synchronization primitives like mutexes, semaphores, and such. So here, in the few coming slides, I want to tell you why that general purpose implementation of synchronization primitives might not be the best you could do if you have a real-time system. So we talked about this previously about priority inversion. So let me actually talk about it in this in the context of real-time systems. So what is priority inversion? So I'm going to define it by an example. Let's assume that you have three tasks with high, medium, and low priority. You could simply assume that you're running rate monotonic scheduler, and this task has an earlier deadline or shorter period than all the other ones. That's how the priorities are assigned. But that's out of the context of this example. The priorities could come from EDF, from LLF, from whatever you name it. So let's say you have priorities this way. And let's say the high priority and medium priority tasks are not yet in the system, so you start running a low priority task. And then at some point, this low priority task locks a mutex. So locks, let's say, resource 1. We don't care, mutex, whatever. So there is a resource that this task is locking. Let's say at time 4, the high priority task becomes available. So it will preempt L and starts running. Let's say at this point, this guy tries to lock R1, but because the resource is already locked by L, this task becomes blocked. So now it's blocked, so it's not runnable anymore. We can go back to running L. So the low priority task continues. This is the first priority inversion that we have. So now we're running the low priority task whilst we could have ran H. So this is the first violation of priorities. Now it gets even worse when, let's say, a medium priority task comes in and executes for a while. So basically now M is going to preempt L and run for a while. Now, if I look at H and M, they have no interdependency on the paper, so they're not using the same resource. But at the same time, M is getting higher priority than H because it's running. So this is the second instance of priority inversion in this case. Now, at some point, this M guy ends, we finish L, and we're basically L releases R1, and we can go back to H, and life continues. Now, this is bad. Why? Because at this point, H is blocked, and it's a high priority task. And we actually don't know how long it's going to take for H to be blocked because of this M guy here. So even though we know L is going to take like a certain amount of time here, we don't know how long this M is going to take. And that could make it really unpredictable for H to have any guarantees on its execution time. And this is called basically priority inversion. Now, there is historical evidence that this has happened in the past. The most famous one is that basically everybody in their courses talk about is the Mars Pathfinder. So the Mars Pathfinder landed on Mars in July 4th, 1997. And immediately after it landed, it started doing experiments and gathering data. Now, this Pathfinder had a single information bus, bus to basically transfer data. And this bus was the shared resource in our case. And it was used by low priority tasks. So this low priority task was an infrequent task that would publish its data. So it would gather data and then publish it to the memory or just push it into the memory using this bus. And it also had, so every time this low priority wanted to use this bus, it would acquire the mutex on this bus to use it. Now there was, other than this low priority task, there were also medium priority tasks in the system. And whenever they would come, the interrupt handler would be fired because it's their scheduling time, and it would put the low priority task to the back of the ready queue and start running medium priority tasks. Now, at some point, there were these high priority tasks that would wake up to see what's going on in the system, right? And these high priority tasks would also use the bus. So they also needed to acquire the lock on the bus. But because the mutex was locked by low priority, they would also go to sleep. Now the system had kind of like a heartbeat checker that would wake up every once in a while and check all the activity in the system and see if everything is all right. Now this guy would wake up and look at the bus, and he would see no transaction on the bus because the low priority task is waiting for medium priority task, and the high priority task is also waiting for low priority task, and the medium priority task doesn't use the bus. So the bus is idle for a while, and that was a bad sign for this heartbeat checker. So at this point, what this heartbeat checker would do, this watchdog, would just reset the entire system, thinking that something really terrible has happened. So it would reset the entire system, and every reset would lead to loss of data. So all the data would be lost. The system would be just reset. And the unfortunate fact about this was that this kept happening. So it didn't happen only once, it kept happening. So the system right after started to experience frequent resets. I think eventually they fixed it. I think remotely they fixed the problem. Anyways, But that's one example that this actually in reality happens. Now, how do we fix it? One way to fix it is, well, we need to work on our synchronization implementation. We need to have some protocol that helps us avoid priority inversion. One way to do it is by using priority inheritance protocol. So this one is very simple. What it does is that every time a low priority task blocks a high priority task, we'll elevate the priority of this low priority task to the priority of the task that this low priority task has blocked. So in this case, in the case of having LMH, if L blocks H, then its priority is elevated to H. So in this sense, M never can interrupt or preempt L. So L will finish, and when L finishes, then H can run. Now, unfortunately, this protocol cannot prevent deadlocks. Here is an example. Let's say you have two tasks, L and H. Let's say L starts, locks, then H comes, it locks another resource, let's say resource 2. And let's say at this time, the H tries to lock R1. Now it gets blocked. You go back to L. You elevate at this point the priority of L. It becomes H. It doesn't really matter in this case because we have only 2. And let's say at this point, L wants to lock R2. So you have a deadlock, right? Because L is waiting for H and H is waiting for L. So in essence, PIP prevents priority inversion, but it creates other problems, most importantly, deadlock. The other thing that it does is that it actually causes chained blocking. Now, chain blocking is also well explained in a picture. Let's look at it. Let's say L starts, it locks R1, then M comes, and it locks R2. And then at this time, it tries to lock R1, it gets blocked. Now I elevate L to M's priority because of PIP. Let's say L continues until H comes. Now H comes in this case. Now let's say H this time wants R2, right? Now R2 is locked by M. So what happens is an M is locked by L. So in essence, at this point, M's priority will become H. So M is going to be elevated to H because H is waiting for M. But then M is also waiting for L. So what happens is that L continues, right? And the moment L releases its lock, because M has inherited H's priority, then M is gonna run. Let's say it acquires R1 and R2. And once it releases R1, then we can let H2 to keep going. Now, if you look at this case, although H didn't really have any resources in common with L, it still had to wait for both L and M, for both of them. So this is called chained blocking. Now, to deal with this, we can implement priority ceiling protocol, which is a enhanced version of PIP, or you could name it a different protocol, but it actually has the priority inheritance. But on top of priority inheritance, we're going to assign priority ceilings to each resource. Now the priority ceiling of I got a question. Isn't this still priority inversion since we make L run before M and H, it is, let me see. So if you look at each individual, right? If you look at the case of L and M, let's say if there was, so you have priority inversion usually when you have 3 tasks. So in the case of L and M, let's say there was another task here between L and M, then implementing PIP doesn't let M wait for this intermediate task, right? So in a sense, M and L are just going to wait for each other. If there is anything in between them, M is not going to wait for this medium one. So in that sense, PIP has prevented M from waiting for anything in between M and L. The same way for H and M, if you have anything between H and M, any task with priority, let's say M and half, whatever, N 1/2, so whatever, I'm just making it up, like medium, high priority, whatever. So again, PIP is preventing H from waiting for this medium task between M and H. So in that sense, it's preventing that. But chain blocking doesn't say anything, sorry, priority inversion doesn't say anything for H and L when they are not sharing any resources, right? So now I have a chain between H, M, and L that priority inversion doesn't say much about because they're on different resources. Priority inversion usually happens on the same resource. When you have a same resource, if you go back to the example with priority inversion, the result is the same, right? With priority inversion and chain blocking, basically your highest priority task will wait for lowest ones. But what causes it is different with priority inversion and chain blocking. With chain blocking, you usually have a chain of resources and tasks that connect them. With priority inversion, you only have one resource that is contentious. Okay, hopefully that answered the question. Now, let's go back to priority ceiling protocol. So what it does, it basically gives a priority ceiling to each resource. I got another question. So you'd think a major bug like that would be discovered pretty quickly in testing, no? Do you happen to know what the conclusion was here? Rover, yeah, did they fire the team? So NASA had more failures, more serious failures than this one. So I doubt anybody got fired, probably depromoted, maybe, I don't know. But I think they fixed it there. So they remotely added priority inversion protocol and updated the software. That's what I think happened. And to be honest, not really. These bugs are hard to catch. They're not really easy to catch. So anyways. Okay, so we're gonna assign a ceiling, and the ceiling of each resource is gonna be the highest priority of any task that can lock this resource. So if we know that this resource is needed by some tasks, we can look at what is the highest priority of those tasks, and then that becomes the ceiling of this resource. Then we're going to actually allow each task to lock a resource if and only if the priority of that task is higher than the ceiling of all resources currently locked by other tasks. So if, let's say, I want to lock resource A, and there are other resources in the system, let's say resource B is locked, already by another task, and I don't actually need R2 at this point. I just want R1. But because R2 is already locked, I'm going to look at the ceiling of R2, and I'm going to compare the ceiling of R2 with the priority of myself. And if my priority is not higher than that ceiling, I won't be allowed to lock R1. So let's look at it in an example. We still have the priority inheritance as well. So let's first see how PCP prevents deadlocks, and then we will talk about chain blocking. So with deadlock, let's say L is running first. So at the beginning, L can lock R1 because no other resources are locked. So we don't need to check anything. Now, at this point, H comes. Now, H wants to lock R2, but then the ceiling of R2 is H because R2 is used by H, so its ceiling is H, and H priority is not higher than H. It's equal to H. So because it's not higher, we're not going to allow H to lock this resource. So we're going to go back to L. L at this point will inherit H's priority. It will lock R1, and at some point it will lock R2 as well, and it finishes. And then we can go to H and let H do its stuff. Oh, there is a... Sorry, this should be R2. Gosh. If I were to guess, it's this color. Maybe higher. Yep. Okay. Sorry about that. So now let's look at an example where priority ceiling can prevent chained blocking. So I'm going to give you the same example that I gave you with PIP. Another should be PCP here. Okay, so L runs. At this point, it can actually lock R1. So let's say M comes. Now M wants to lock R2, but then R2's it gets blocked because M is not higher than ceiling of R1. So the ceiling of R1 is H because I think H also wants it. So at this point, M will be blocked. We will go back to L. L inherits M's priority. Let's say H comes at this point. Now H wants to acquire R2. Well, it's not higher than the ceiling of R1 again. So it will be blocked. We'll go back to L. L finishes at this time. It releases the lock. We'll go back to R2 and things continue. I think here the ceiling of R1 is M because M also wants R1. So the ceiling of R1 is M, and at this point M is not higher than M. That's why M gets blocked. So at this point, if you can see here, now H is only waiting for L, not M. So we basically broke the chain. We don't let H to wait for both L and M as it was with chain blocking. So I got a question, why is it a good thing that H can never lock R2? Because we are preventing deadlock, right? It's not that H can never do it. It actually can, as you can see here, because so at this point, why do we allow H to lock R2? Because there is no other resources locked. So at this point, H can lock R2 because there is no other locked resources. So we don't need to check H's priority with R2's ceiling. So we allow H to lock R2. So it's, your question is not that accurate. So we're allowing it, but it just depends on when we're allowing it. Okay. So EDF can, the priority inversion basically can happen with EDF. In the context of EDF, we call priority inversion deadline interchange because priorities are identified by deadlines. So if you have priority inversion, you basically have deadline interchange. So a task with an earlier deadline has to wait for a task with a deadline in future. And the way to deal with it is to change priorities. Well, in the context of EDF, you can just change the deadlines. And by changing deadlines or basically exchanging deadlines, you can bring the deadline of the task, the low priority task, to become a high priority task. Okay, now let's have 2 minutes of break, and then I'll continue the rest of this lecture on multiprocessors. Okay, let's keep going. So this slide is going to be our gateway into talking about multiprocessors in real-time systems. And the issue of multiprocessors is just going to add another level of challenge to real-time systems, as we'll see. Okay, so in uniprocessors, it's kind of accepted if high priority task preempts lower priority ones, right? That's basically what we sort of want. But this is not necessarily a desirable property in multiprocessors. You might think it should be, but let's look at an example that that gives you a perspective on why you might not want to let high priority tasks to preempt low priority tasks. Let's say you have a multiprocessor with 2 CPUs. Let's say for load balancing issues or whatever reason, you have put a high priority task and a low priority task on CPU 1, and you have a medium priority task on CPU 2. Now, let's say this is your schedule for CPU 1. I haven't shown you what happens in CPU 2. Let's just look at it. Let's say you were running L. At this point, L locked R1. At this point, H arrived on CPU 1, became schedulable, and it preempted L until it was done. Then L started running, then it unlocked resource 1, and it finished. So far so good. If we only had one CPU, this was perfectly fine. We would say, okay, H should indeed preempt L. Everything is fine. Now let's look at CPU 2. Let's say while we were running L, let's say we were also running M on CPU 2. And let's say at this point, M wanted to lock R1. But because R1 was locked by L, M gets preempted or blocked. It doesn't get preempted, it gets blocked, right? And it gets blocked until here L unlocks R1. So then M can run. Now, if you give it some thoughts in this scenario, it might have been okay if H only blocked L, but is it okay for H to basically indirectly block both H and M? What that means is basically, is L plus M lower than H, or is L plus M higher than H? So as you can see, it's kind of like a gray area. So I got a question: how is the priority ceiling for a resource assigned, and by whom? So priority ceilings are assigned by, if you want to implement basically priority ceiling, by the protocol. So you would implement the protocol. So you would implement PCP protocol, and then you would provide APIs for the threads that want to use this protocol. And that API would make every thread to announce prior to its execution what resources it needs. Very much similar, if you remember ECE 252 with deadlock prevention. You would say what resources you want at max before you start executing, right? So this is very similar. If you really want to implement PCP, you would provide such an API that would allow threads to, prior to their execution, tell you what resources they want, and that gives the protocol a mean to assign priority ceilings. So once you know what tasks need a particular resource, then you can assign ceiling for that task. Hopefully that answered the question. Okay, so going back to the multiprocessor case, as you can see, here we have a decision to make, really, and it's actually, it would depend on what H is, what L is, and what M is. Maybe in your case, it actually makes sense. H is really high priority, and it's more important for your system than M and L combined. But in some other scenarios, it might not be the case. You might say, okay, H is greater than L, H is greater than M, but H is not greater than L plus M. So in those cases, you have to actually do something else. Okay, now that brings us to the issue of, okay, how do you actually schedule a multiprocessor for a real-time system? Now, there are three categories, if you wish, three main categories, very similar to what we saw with general purpose operating systems. You could go with the partitioning category. Basically, this means that you're going to partition your tasks between CPUs. So each task will be assigned to a CPU, and this task cannot migrate anywhere. This task and all its jobs will be executed on this CPU. So this is one way you can look at it. So this basically solves your problem. Now you just pick a uniprocessor scheduling policy, and after you partition your tasks, now each CPU knows its tasks. It just independently schedules its tasks. The other way to do it, you can allow migration, but restrict them. What does that mean? So you could, instead of assigning tasks, you could assign jobs. So remember, jobs are units of tasks that would appear every period. Now you could say, I'm going to assign, instead of assigning the entire task and all of its jobs to a CPU, I want to assign each job to a CPU. So each job will be assigned to a CPU and cannot migrate. And if you want to go further, you could actually allow jobs to also migrate. And that gives you full migration. So allowing jobs also to migrate. So as you can see, this is basically load balancing stuff that we were talking about. So with no migration, you have no load balancing. You have to do your best to partition your tasks at the beginning, but then once they start running, you cannot load balance. So everything you want to do should happen prior to execution. Here you're allowing load balancing, but in a restricted way. Here you can load balance as much as you want and with whatever granularity you want. So given that, I can have this this table here. So we're still going to talk about online schedulers. So we had the static scheduler, dynamic schedulers, and fully dynamic schedulers. So these ones would assign same priority to tasks. So static priorities. These would assign fixed priorities to jobs. And these would assign dynamic priorities to jobs. And now on each column, I'm going to put no migration, restricted migration, and full migration. And now each one of these cells is one scheduler class. So if you remember the scheduling classes for uniprocessor is basically just this, static, dynamic, fully dynamic. Now, if you have a multiprocessor, depending on whether or not you allow migration, you add more classes. Now let's look at some of these classes. So looking at this class, basically no migration. So no migration, now it doesn't really matter what the first element is, a static, dynamic, or fully dynamic. What can we say about these? So first of all, no migration means that you have to partition your tasks. And finding the optimal partitioning is NP-hard problem. Basically finding the partitioning that would lead to all tasks meeting their deadlines and achieving the lowest execution time possible is NP-hard. So you cannot wish to solve or come up with optimal schedulers in these classes. So this actually is 3 classes. Now, there are several polynomial time heuristics for these cases. Very similar to what you've seen with memory allocation. You can do best fit. Basically, for each task, you can look at all the, so you can iteratively assign your tasks to CPUs and keep track of how busy each CPU is. And then you can assign your task to the best CPU in terms of whatever metric you have. Or you can, or first one that fits it. So the first one that can accept this and still meet the deadlines, you can assign it. Or you can actually look for the best CPU, basically looking for the one with minimal remaining space capacity. With this best fit, your purpose is to consolidate tasks on CPUs. So you want to make one CPU full capacity before you move to another CPU to fill it up. And so on and so forth. So you can just come up with polynomial time heuristics. The bad thing about it is that there is no guarantee. And the worst thing about it is that there is a theorem that says the worst case utilization that you can achieve is m+1 divided by 2. Here, m is number of CPUs you have in your system, and n is number of periodic tasks you have. This basically says you can have a task set that no matter what you do, no matter what partitioning algorithm you choose, the utilization of each CPU is going to be m+1 divided by 2. So basically very low utilization of CPUs. Here is an example. So let's say you have m+1 tasks. So n equals m+1. And let's say that let's say that execution time of each one of them is 1 plus epsilon, and the period of each one is 2. So each one of them has a period of 2, and their execution time is 1 plus epsilon. And how many of them do you have? m+1. How many CPUs do you have? You have m, right? So if you dual yourself on this question, the best you can do is to run m tasks on m CPUs. So all of them would meet their deadlines, right? But they all would finish at time 1 plus epsilon. Now at time 1 plus epsilon, all the CPUs now until time 2 have 1 minus epsilon time remaining, and you still have one task to meet. And no matter where you assign this task, it's going to miss its deadline. So no matter what partitioning algorithm you use, this task set is not schedulable, right? And what is the utilization of this task set? It's basically m+1 divided by 2. It has an epsilon, but that epsilon is, if this epsilon is small enough, then it gets as close as you want to m+1 divided by 2. And this is basically really bad, right? Because you would imagine if you have m CPUs, you can schedule task sets that have a utilization of all the way up to m, because you have m CPUs. But this tells us that for these classes of schedulers, the best you can do is m+1 divided by 2, like having a firm guarantee. So I just showed you a task set with a utilization of almost half of what your system is capable of, and you still cannot schedule this scheduler, no matter what scheduling policy you choose. How much time do I have left? Oh, I'm already done. Okay. So yeah, I guess really wanted to finish the slides. How many slides? Okay, it's fine. So we'll hopefully finish on Monday and start talking about memory management. Okay, so with that, I'm going to end this lecture. Thank you for those who attended. Take care and be safe. Bye-bye.